So you're using artificial intelligence, I mean, every single day, right? Maybe you don't even realize you've just pinged some massive neural network.
Oh, absolutely. It's everywhere.
Is your GPS rerouting you in real time? It's the show that pops up in your streaming queue, or, these incredible image generators that are everywhere now.
All of it.
And these systems, they aren't running on magic. They are running on math. And the engine, the real fundamental engine behind all of modern deep learning, is calculus.
But probably not the calculus you remember from school.
No, definitely not. This is its much bigger, more complex, multi-dimensional cousin. Today, we're doing a deep dive right into that mathematical core. We're looking at two things. First, the tool that lets you handle millions of variables at once, matrix calculus. We'll be talking gradients and Jacobians.
And second, and this is crucial, the little function units that give these systems their real power to decide things, the activation functions.
Exactly. So our mission today is to be your shortcut. We're going to pull back the curtain on things like PyTorch and TensorFlow and show you what's actually happening under the hood when an AI model is training. It's a kind of beautiful dance of differentiation.
And you really need to understand this. It's so tempting to just, let the frameworks handle it all with automatic differentiation.
Yeah.
But when your model breaks, or when you need to really optimize a new architecture, or you're just trying to read a research paper, you have to have mastered this.
Yeah.
You need to get past thinking about the slope of one line and start thinking about measuring change across these huge high-dimensional vector fields.
That sets the stage perfectly. So let's start with that big picture. Why calculus? Why is the study of change so essential here? When we say we're training a neural network, what are we really doing mathematically?
Functionally, training a network just means finding the best possible set of parameters, the weights and the biases. We want to find the exact set that lets the network do its job, whatever that is, most accurately.
So if it's sorting pictures of cats and dogs, it gets the labels right.
Exactly. And to figure out how good any set of weights is, we use something called a loss function.
A loss function.
You can think of it as a measure of unhappiness or error. It takes what the network just predicted, compares it to the real answer, the target, and it spits out a single number.
And you want that number to be as low as possible.
As close to zero as you can get. A loss of zero means the network is perfectly happy, perfectly accurate.
Okay, so if the network needs to get happier or less unhappy, it needs a way to get that loss number down. It sounds like you're trying to find the bottom of a huge, foggy valley.
That is the perfect analogy. You're standing somewhere on the side of this valley, which has millions of dimensions, one for each parameter.
And you can't see the bottom because of the fog.
Exactly. The fog is the sheer complexity. So since you can't just look and see the lowest point, you only have one tool. You can feel the ground right under your feet. You have to figure out which direction's downhill.
And that's where calculus comes in.
That's where calculus comes in. To minimize that loss, deep learning uses different versions of gradient descent. It's a simple idea, really. You calculate the slope right where you are, take a small step downhill, and then you do it all over again.
And that slope, that's the gradient, which means you need the derivative.
Precisely. All of these optimization techniques, whether it's plain old stochastic gradient descent or SGD, or things that help smooth out the journey like SGD with momentum, or even the really advanced optimizers like Atom, they all need one piece of information.
The gradient,
which is just a big vector containing the partial derivative of that loss function with respect to every single weight and bias in the entire network.
So you're asking for every single knob I can turn. If I tweak this one knob just a tiny bit, how much does my total unhappiness change?
That's it. And that vector, the gradient, it actually points in the direction of the steepest uphill slope, the steepest ascent.
So the network just does the opposite. It goes in the direction of steepest descent.
Exactly. The gradient is the compass. And the goal is just to keep adjusting all those weights and biases step by step in the direction opposite the gradient so that the total loss keeps getting smaller. That continuous adjustment based on measured change. That's why calculus is the absolute foundation of AI training.
Okay, before we dive into calculating gradients for millions of parameters, we probably need a quick refresher, because the complexity of matrix calculus is all built on the simple rules of single variable differentiation, right?
It is. Let's do a quick speed run, like the 60-second version of the rules we absolutely need.
Let's do it.
Okay, first, if your function is just a constant number, its derivative is 0. No change, no slope.
Makes sense.
If you multiply a function by a constant, say 5 times x squared, the derivative is just 5 times the derivative of x squared. The constant comes along for the ride.
And the big one, the power rule.
the workhorse. For any x to the power of n, the derivative is n times x to the power of n minus 1. And because this is all a linear operation, if you're adding or subtracting functions, you just take the derivative of each part separately, the sum and difference rules. It lets us break down big problems.
Okay, so that's the basics. Now let's layer on the complexity that networks actually use. We've got nested functions, functions multiplied together. That brings us to the product rule.
Right. When you multiply two functions, let's call them f and g, the derivative is f times the derivative of g plus g times the derivative of f.
And then the most important one, the one you said is like the ancestor of backpropagation.
The single variable chain rule. This is the concept we have to get.
Yeah.
If you have a function inside another function, like f of g of x, you take the derivative of the outer function and you multiply it by the derivative of the inner function.
So you're kind of tracing the influence backwards.
Yeah.
You see how much a little nudge in x changes g, and then you see how much that change in g nudges the final output, f, and you multiply those effects together.
That's a perfect way to put it. You're multiplying the rates of change. If you're calculating the derivative of, say, the natural log of x squared, you find the rate of change of the log function and multiply it by the rate of change of the x squared part. And this exact principle, this multiplication of rates, holds up even when we scale to a network with millions of parameters.
Okay, now for the leap. We're moving from one variable to many. In a neural network, you could have thousands of inputs changing all at once. How on earth do you measure the slope in a 10,000 dimensional space?
You use the partial derivative. It sounds intimidating, but the idea is simple. If your function depends on a bunch of variables dashed by 1, by 2, by 3, and so on, the partial derivative with respect to y1 just means you pretend for a moment that all the other variables are constants. You freeze them.
So you're just measuring the slope along one single axis at a time.
Precisely. And once you've done that for every single input variable, you collect all those partial derivatives and you bundle them together into a vector. That vector is the gradient. You'll see it written with that little triangle symbol in the block.
So for our example, if the function f of x and y equals 5x squared y, the gradient is a vector with two parts. The partial with respect to x and the partial with respect to y.
Correct. So to get the partial with respect to x, you treat y like a constant. The derivative is 10yx. Then, for the partial with respect to y, you treat x as the constant. The derivative is just 5x squared.
So the gradient vector is just 10yx 5x squared.
Exactly. And that vector points in the exact direction you'd need to move both x and y to get the biggest possible increase in the function's value, the steepest path up the hill.
Okay, that makes sense for one output, like a single loss value, but networks can have multiple outputs, right? Like predicting the probabilities for 10 different classes of images. How do you track change when you have multiple outputs and multiple inputs?
For that, you need to generalize the gradient. And that generalization is the Jacobian matrix.
The Jacobian?
It's just a way to organize all the possible cross-influences. If you have, say, m different output functions, and each one depends on n different input variables, the Jacobian matrix captures all of it.
So in the source example, we have two output functions, f and g, and two inputs, x and y. So the Jacobian J should be a 2x2 matrix.
That's right. And the structure is just, you stack the gradients.
Exactly.
The first row of the Jacobian is the gradient vector for the first output function, f. The second row is the gradient vector for the second output function, g.
So for our example, row 1 would be the gradient of f, 10yx 5x squared, and row 2 is the gradient of g, 5, 8y to the 7th.
And that single 2x2 matrix now holds everything. It tells you the rate of change of every single output with respect to every single input. More generally, if you have an output vector y that's a function mapping n-dimensional space to m-dimensional space, the Jacobian is an m by n matrix.
Right, the intuition here feels important. The m rows are the m different outputs that can change, and the n columns are the n different inputs that are causing the change. It's really just an organizational tool. It's for efficiency.
It's pure efficiency. Instead of calculating m different gradients one by one, you calculate them all at once and store them in this one object. And this matrix is exactly what we're going to plug into the vector chain rule.
Here's where it gets really interesting. We're moving from the pure math to how this is actually built. Neural networks are just chains of functions applied to vectors and matrices. So we need tools that can calculate derivatives across all this data at once.
And very often, the operations we're doing are applied to every element of a vector in the same way. We call this an element-wise operation.
Like applying the ReLU activation function.
Exactly. You apply it to every number in the vector at the same time. Now think about what that means. If you have an output vector, y, that depends on an input vector, w crick, and the operation is element-wise, then the ith component of the output, yi, only depends on the ith component of the input, wi.
Ah, so it doesn't care about any of the other elements. That must make the Jacobian way simpler.
Massively simpler, because when you calculate that Jacobian matrix, JW, you're looking at the partial derivative of every output yi with respect to every input wj. And if I is not equal to j, that derivative is just 0.
So the matrix is mostly empty.
Right. The resulting Jacobian is a diagonal matrix. All the non-zero values are on that main diagonal. This is a huge deal for performance. Storing and multiplying these sparse matrices is so much faster. The very structure of neural networks is designed to take advantage of this.
Okay, what's next? The idea of vector sum reduction. This has to be critical because at the end of the day, you need to boil everything down to that one single number, the final loss value.
Yes. The loss, y, is usually the sum of some function applied to a vector of inputs,
Yep.
x. And because the output y is a single number, a scalar, its derivative with respect to the input vector x isn't a matrix anymore, it's just a row vector.
This is the final gradient that you use to update the weights.
This is it. And the key idea here is that summation. If you want to know how much one single input, say xj, influenced that final sum y, you can't just look at one path. You have to sum up how xj contributed to every single intermediate part of the calculation.
So you're adding up the influence across all these parallel paths. If my input xj affects 5 different things, and all 5 of those things get added up to make the final score, then the total influence is the sum of those 5 individual influences.
That's it, exactly. Mathematically, the partial of y with respect to xj is the sum over all I of the partials of fi with respect to xj. This is really the first hint of how backpropagation works. Influence is cumulative. It gets added up as you trace it backwards.
Which brings us to the ultimate tool, the thing that ties it all together, the vector chain rule. This is backpropagation.
This is the mathematical engine of backpropagation. Well, the bridge is the idea of the total derivative. In the simple case, one variable affects an intermediate, which affects the output. We multiply. In the multivariate case, one input can affect multiple intermediate variables, and all of them can affect the final output. So you have to sum up all those different paths of influence.
Okay.
And the really beautiful insight for deep learning is that this whole complex process of summing up partial derivatives, it's mathematically identical to simple matrix multiplication when you use Jacobians.
Wait, really?
Yes. If you have a nested function f of g of x, where these are all vectors representing network layers, the overall Jacobian is just the Jacobian of f with respect to g, multiplied by the Jacobian of g with respect to x.
So the change at the output layer is calculated. That's one matrix. And you
Right.
just multiply it by the matrix that represents the change in the middle layer. That multiplication is what sends the error signal backwards through the network.
And the dimensions have to line up perfectly. Say the final output f has m components, the input x has n components, and the intermediate layer g has k components. The first Jacobian, the partial of f over g, is an m by k matrix. The second one, partial of g over x, is a k by n matrix. And when you multiply an m by k matrix by a k by n matrix, you get an m by n matrix.
Which is the exact right size. M outputs and inputs. The math just works. It's a consistent, incredibly fast way to calculate the influence of every single input on every single output, no matter how many layers you have.
The single formula.
You good?
This is the heart of backpropagation. Every time a framework trains a model, it's just doing a long chain of these matrix multiplications, governed by this one elegant rule.
So now that we have the math of how change flows through the system, let's zoom in on the thing that's actually doing the work. The artificial neuron, the basic building block.
The structure is actually quite simple. It's meant to mimic, in a very basic way, a biological neuron. You have a set of inputs by 1 through xn. Each of those inputs gets multiplied by a weight, w1 through ever. Think of the weight as its importance.
Okay.
All of those weighted inputs are added together, along with one extra constant term, the bias.
Right, the bias.
That first step just gives you a single number, the weighted sum. People usually call it z. But here's the critical part. That number, z, is then passed through an activation function, let's call it g. And the output of that is the neuron's final signal, its activation, a.
And for this to be efficient, we can't be writing out w1 times by 1 plus w2 times by 2. We have to use vectors.
Always. You must use vectorized notation. The weighted sum z is just the dot product of the weight vector w and the input vector x. We write it as w dash transpose dash x. So the final output is just a equals g of w dash transpose dash x. That's it.
A linear step, the dot product, followed by a nonlinear step, the activation.
That simple combination is the power unit of all deep learning. And for a long time, that function g was almost always the logistic sigmoid function, which we'll get into.
So we take these units and we stack them into layers: input, hidden, and output. That's the neural network.
Exactly. It's a collection of these neurons, or nodes, where the output of the neurons in one layer becomes the input for the neurons in the next. The connections between them are where the weights live. Those are the parameters that get learned.
And the type of network we're talking about here is a feed-forward network.
Yes. For now, yes. In a feed-forward network, the information only moves in one direction, from input through the hidden layers to the output. There are no loops, no going backwards. It's a clean, sequential cascade of calculations.
So let's make that concrete. Let's walk through a small 3-layer network, but do it the way a real library would, with vectors.
Okay, let's say layer 1 is our input vector, x. Layer 2 is the hidden layer, and it'll produce an activation vector, a 2. Layer 3 is the output, a 3. To connect them, we need two weight matrices.
W1 and W2.
Right, W1 connects layer 1 to layer 2. If you have, say, 4 inputs and 3 hidden neurons, W1 is a 3x4 matrix. W2 connects the hidden layer to the output. If there's one output neuron, W2 would be a 1x4 matrix, assuming you add a bias to the hidden layer activations.
So if I feed my input vector x into this system, how do I get the output of that entire hidden layer in just one step?
Matrix multiplication. The vector of weighted sums for the hidden layer, which we'll call Z2, is just the weight matrix W1 multiplied by the input vector x.
So Z2 equals W1 times x, and that one operation does the calculation for all 3 hidden neurons at once.
Simultaneously. Then, the activation vector for that layer, A2, is just the activation function g applied element-wise to that Z2 vector. Then you repeat the process.
Right. The next weighted sum, Z3, is the next weight matrix, W2, multiplied by the hidden layer's activation vector, A2.
And the final output of the whole network is just g of Z3. This compact, vectorized process is what allows GPUs to handle networks with billions of parameters. It all boils down to these massive parallel matrix multiplications.
We've talked about this process. Input times weights gives you a sum, and that sum goes through an activation function to give you the output.
Yeah.
And that second part, the activation function g, it feels like that's where the magic is. Why can't we just not have one? Why not just use the sum directly?
That's a great question, and the limitation is huge. If you only used a linear activation, or no activation, which is the same thing, then stacking layers would be completely pointless.
Why?
Because a linear function of a linear function is still just a linear function. You can stack 100 layers, and the whole network would collapse down into a single, complicated, but still fundamentally linear model.
So you'd basically just have a very fancy version of logistic regression.
Precisely. It could only learn to separate data with a straight line or a flat plane.
Mm-hmm.
But the real world is almost never that simple, right? Your data might be in a spiral or a circle. No straight line can classify that properly.
The world is nonlinear.
Yeah. The world is nonlinear. So we need networks that can build complex curved decision boundaries. The activation function g is what introduces that necessary nonlinearity. It bends and warps the space, allowing the next layer to learn things the previous layer couldn't. Without it, deep learning just wouldn't work.
So let's look at the big three, the most common activation functions.
Okay, we have to start with the historical one, the logistic sigmoid. Its formula is 1 over 1 plus e to the negative x. And it gives you that classic S shape. It squishes any number, no matter how large or small, into a range between 0 and 1.
Which was useful because you could treat the output like a probability.
Exactly. Then you have the hyperbolic tangent, or tan. It's a very similar S shape, but it's actually just a rescaled sigmoid.
Yeah.
And its output range is from -1 to +1. That's a key difference because it means it's symmetric around 0, which can help with training.
And then there's the modern champion, the one you see everywhere.
The rectified linear unit, ReLU. And its definition is almost ridiculously simple. The function of x is just the maximum of 0 or x.
So if the input is positive, the output is just the input. If the input is negative, the output is 0.
That's it. It's just a hinge at 0.
So when ReLU came along, it doesn't sound as mathematically neat as the smooth sigmoid curve. Why did this simple hinged function completely take over and push sigmoid out of deep networks?
It solved a crisis, a really big one. The vanishing gradient problem. This was the thing that was holding back deep learning for years.
The vanishing gradient.
Look at the graph of the sigmoid function. When your input x gets very large, either positive or negative, the curve becomes almost perfectly flat.
Right, the slope goes to 0.
The slope, the derivative, goes to 0. Now remember the vector chain rule. Backpropagation works by multiplying all the derivatives from all the layers together.
Ah.
If you have a deep network and a few of your layers have activations that are in that flat part of the sigmoid, their local derivative is basically 0. So when you multiply all these numbers together in the chain, the whole product goes to 0.
The gradient just vanishes. It's like sending a message down a long line, but every person whispers it so quietly that by the end, there's just silence.
That is a perfect description. The signal dies. And that means the weights in the early layers of the network get almost no update signal. They just stop learning. And this made it practically impossible to train very deep networks. They just wouldn't improve.
So how did ReLU fix it?
With brute force simplicity. For any positive input, the function is just f of x equals x. The derivative of that is 1.
The constant.
A constant gradient of 1. It's not 0. So the error signal can flow backwards to the positive side of the network without getting weaker. It just passes the signal straight through. And that one simple property allowed researchers to finally train networks that were dozens, even hundreds of layers deep.
So that was the turning point. It's less about mathematical elegance and more about practical stability for training. The advice is clear: don't use sigmoid in your hidden layers anymore.
Absolutely not. Now, ReLU isn't perfect. It has the dead neuron problem, where if a neuron's input is always negative, its gradient is always 0, so it also stops learning.
Right.
And that led to things like leaky ReLU, which has a tiny slope on the negative side to keep it alive, but that's a whole other deep dive. I will say, just as a neat mathematical side note, there is a smooth version of ReLU called Soft Plus, and its derivative, very conveniently, is the logistic sigmoid function. They're all connected.
So what does this all mean? We have this simple neuron, we've given it nonlinear power with activation functions, and the real magic happens when you start putting them together. It turns out this system can solve incredibly complex problems, starting with something as basic as logic gates.
Exactly. You can show the power of just one nonlinear neuron by building a Boolean ADD gate. We use the sigmoid function. We want the output to be close to 1, only when both inputs by 1 and by 2 are 1.
Okay, how do you set the weights?
You can set the bias to the neck is 30, and the weights for by 1 and by 2 to plus 20 each. So your sum, z, is minus 30 plus 20 times by 1 plus 20 times by 2.
Let's check that. If both inputs are 0, z is negative 30. Sigmoid of negative 30 is basically 0. Correct.
If one is 1 and the other is 0, z is negative 30 plus 20, which is negative 10. Sigmoid of negative 10 is still very close to 0, also correct.
But if both are 1, z is negative 30 plus 40, which is plus 10, and the sigmoid of plus 10 is almost exactly 1. Wow, okay, so it works. It's an A and D gate.
And you can make the other gates just by tweaking the weights and bias. For an OR gate, you just make the bias less strict, maybe negative 10. For a NOT gate, you give it a positive bias and a big negative weight to flip the logic.
But all those gates and D, or not, they're all linearly separable. You can draw a single straight line to separate the trues from the falses. The real test, the one that shows why you need more than one neuron, is the XOR function.
The XOR, or its opposite, XNOR. That's the classic problem. XNOR is true only when the inputs are the same, both 0, both 1. And if you plot those 4 points, you realize there's no single straight line you can draw to separate the true points from the false points.
It's not linearly separable.
It's not. And that's why you need a network with a hidden layer. This little problem proved that hidden layers are necessary to combine simple representations into complex, nonlinear ones.
So walk me through it. How does a two-layer network solve XNOR, a problem that's impossible for a single neuron?
The hidden layer basically learns to create 2 different simpler regions, and the output layer learns to combine those regions.
So you have 2 hidden neurons. What does the first one do?
The first hidden unit can be trained to implement the OR function we just talked about. So it fires, it outputs a 1 if either input is 1.
Okay.
The second hidden unit can be trained to implement something like not by 1 and not by 2. So it only fires if both inputs are 0.
So one hidden neuron has carved out a space for the 0, 0 point, and the other one has carved out a space for the points where at least one input is 1.
Exactly. Now the output layer just has to learn a simple rule based on the signals from those 2 hidden neurons. It learns to say, I will fire only if the second hidden unit is firing, or if both inputs are on. By combining those 2 simple linear boundaries from the hidden layer, the network as a whole creates a complex, nonlinear decision boundary that perfectly solves the XNOR problem.
That one small example really shows why layers are so powerful. It's about building complexity on top of simplicity.
It is.
And this ability to solve XNOR hints at something much bigger, doesn't it? The universal approximation theorem, what does that theorem tell us?
It's the theoretical bedrock of why deep learning is so powerful. It was proven by George Sigenko, and it states that a neural network with just one hidden layer, as long as it has enough neurons, can approximate any bounded and continuous function.
Any function.
Yeah.
That is an incredible claim. So whether you're modeling fluid dynamics or the stock market, in theory, a single hidden layer network can learn that pattern.
In theory, yes. The big catch is given enough units. To solve a really complex problem, you might need an exponentially large number of neurons in that one layer, which would be impossible to actually train.
Ah, okay.
But the theorem gives us you increase the capacity with more layers and more units. And while the theorem says one layer is enough, in theory, in practice, adding depth more layers is a much, much more efficient way to build up that capacity to model the complex, nonlinear world.
This has been an incredibly detailed journey. We've really traced the path of calculus in AI. We started with simple derivatives, scaled up to the Jacobian matrix that measures all changes at once, and then saw how the vector chain rule uses matrix multiplication to send signals backward through the network.
The engine of backpropagation.
Exactly. And then we saw that it's the activation functions that give these linear systems their nonlinear power, turning them into universal approximators that can solve problems like X and OR. And for you, the listener, the takeaway here is that training an AI isn't a black box anymore. You now know it's a constant mathematical process of calculating a gradient and then nudging millions of parameters step by step to lower that score of unhappiness, the loss function.
To really boil it down, I think there are three key takeaways from this deep dive.
Let's hear them.
First, derivatives are the compass. The gradient is the one tool you need for optimization. It tells the network which way is uphill on the loss function, so it knows to take a step in the opposite direction.
Right.
Second, matrix calculus is the language of deep learning. You have to understand the vector chain rule. Realizing that backpropagation is just a series of Jacobian matrix multiplications is the key to understanding how all the automated tools work under the hood.
And third,
Nonlinearity is non-negotiable. You have to have it. Activation functions like ReLU are what give networks the power to model the real world. And just as importantly, they solve critical performance problems, like the vanishing gradient, that allow us to build the massive deep networks we have today.
we talked a lot about how training follows the gradient downhill to minimize loss. But here's a final thought to leave you with. In a landscape with millions or even billions of parameters, that gradient only tells you the slope right where you're standing. So how do these systems find an efficient path all the way down to a good solution without getting permanently stuck in a bad spot, some little ditch on the side of the mountain, or just wandering around for 1,000 years? That crucial next step, the strategy for actually navigating that incredibly complex landscape, that's exactly what we'll unpack next time.